Hi Bobcats! In this video we're going to look at something known as Dalton's Law of partial pressures. Dalton's Law is used to describe gas mixtures in terms of the partial pressures of each gas. This is a very practical thing. When you're handling gases in lab, you typically have some sort of a reaction container that then is attached to various cylinders of different types of gases, and you have some sort of a pressure gauge on your system so that you can monitor what the pressure is. And so typically you will add gas to your container and monitor the pressure, and you know based on the pressure then how much gas you added. All of these gases are going into the same container, so their volume will all be the same and their temperature will be the same. The thing that will be different is the pressure exerted. If you have just a little bit of one gas, those few gas particles collide with the walls of the container, exerting just a little bit of pressure. And then if you have a lot of another gas, those lots and lots of gas particles are colliding very often with the walls of the container, exerting more pressure. So when we start talking about mixtures of gases, just based on the practicality of how we set up reactions, this is how we're going to talk about those mixtures. We'll talk about the pressure exerted by each part of your mixture of gas. The mathematical statement of Dalton's law of partial pressure is that the total pressure exerted by all of the gases in a mixture is equal to the sum of the partial pressures. So let's say you have a mixture of helium and neon. P1 might stand for the partial pressure that's due to helium, and then P2 might stand for the partial pressure that's due to neon. As we're working with these gas mixtures, the concentration of one gas compared to the whole is sometimes expressed in terms of mole fraction. This is another concentration unit in addition to the one we already learned, which was molarity. And so mole fraction is abbreviated with a capital X. So yeah, mole fraction, I really probably should have written up here in the title, mole fraction, comma, X. Mole fraction is given by the number of moles of a component, so whatever unknown gas A is, like if that's helium, that's how many moles of helium you have, divided by the total number of moles. Dalton's law is also sometimes expressed in terms of mole fraction, which tells us that the partial pressure of one gas is equal to its mole fraction times the total pressure in the container. Sometimes it might be useful to rearrange this equation just a little bit as well to solve for the mole fraction of a particular gas, and that's going to be equal to the partial pressure of that particular gas divided by the total pressure in the container. So as our first example involving a calculation with Dalton's law, we're given that the mole fraction of oxygen in dry air is about 0.21. What is the partial pressure of oxygen in a sample of dry air that has a total pressure of 761 millimeters of mercury? Well, if we want to know what that partial pressure of oxygen is, it's going to be equal to the mole fraction of oxygen times the total pressure in the system. So the mole fraction of oxygen was given as 0.21, and the total pressure was given as 761 millimeters of mercury. So let's grab a calculator and run those numbers through. I've got 0.21 times 761, and that's giving me a numerical value of 159.81. So since our mole fraction only has 2 sig figs, I should probably round that to 160 millimeters of mercury. A very practical lab application of Dalton's law is when you generate a gas in lab and you collect it over water. This system is really helpful because it prevents anything from getting pressurized. You have your reaction container, which is this test tube, and as gas gets generated, it exerts pressure and that gas pushes through this tube, and then that tube gets inserted into this upside down bottle that's been filled with water, and as that gas pressure increases, the gas starts to bubble up into this jar and displaces the water. This keeps everything equilibrated at atmospheric pressure, so you don't run the risk of anything blowing up because you're overpressurizing it. But when you do this and this gas starts bubbling through water, some water will evaporate into the gas. We normally refer to that as humidity. So that gas that you're collecting, even though on this diagram it's labeled oxygen for that gas that's collecting at the top of this container, it's actually a mixture of oxygen with a little bit of water vapor inside of it. So in this example, we're going to have to take that water vapor into account. Millimole is using a reaction setup like we saw in the previous slide, and she collected her gas over water. We have the temperature that she was at and the current pressure. That she measured the pressure by using the weather service, and I did the conversion for you from 30.06 inches of mercury over to 764 millimeters of mercury. But what she really needs to know is the partial pressure of hydrogen, because that's telling her how much hydrogen gas she generated and was collected in her apparatus. But the gas that she collected is actually a mixture of hydrogen and water because of that water vapor that evaporated as part of the experimental process. So if you go to the Sapling Learning Compendics, you can look up the vapor pressure of water at different temperatures. So we want to go down to our temperature, which is 25 degrees C, and catch what the vapor pressure of water is. Now, according to Dalton's law of partial pressure, the total pressure in this scenario should be equal to the pressure of the hydrogen gas that she generated plus the pressure due to this water vapor. So her total pressure was 764 millimeters of mercury because it's all equilibrated with the atmosphere. The pressure of hydrogen is what we're trying to find, and the vapor pressure of water is 23.756. So to get the pressure of hydrogen all by itself, I'm going to take 764 and subtract 23.756. So if I run that through my calculator, 764 minus 23.756, that is giving 740.244. And I think sig fig wise, we really should round that to the nearest whole number. So that's going to be 740 millimeters of mercury that are due to hydrogen gas. That vapor pressure data came from the Sapling Learning Compendics. If you've not already bookmarked this site on your browser, you probably want to add it. That will get you to all of the constants that Sapling Learning has posted, including like heats of formation tables, densities, any sort of data that you might need for any of your homework or quiz or test calculations. So our objective for this video was to describe gas mixtures in terms of the partial pressure of each gas. And to do that, we use Dalton's law, which says that the total pressure is equal to the sum of the partial pressures due to all of the gases that are present in a mixture. And we sometimes characterize this in terms of mole fraction. The partial pressure of one gas is given by the mole fraction of that gas times the total pressure.